Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to session 1, Learning by Solving Problems on Alcohols, Organic Chemistry 1. Reduction of the ketone group of negative menthone, which has its alkyl groups trans to one another, gives two products known as negative menthol and positive new menthol. These two substances differ considerably in their reactions. Positive new menthol undergoes dehydration either in methanoic acid or when treated with phosphorus pentachloride, whereas negative menthol gives a methanoate ester with methanoic acid and a chloride with phosphorus pentachloride. What is the relation between new menthol and menthol, and why do they behave differently with methanoic acid and phosphorus pentachloride? What is likely the structure of the menthene from the dehydration of new menthol? Here is the structure of menthol, where we have methyl and isopropyl trans to one another. Drawing the structure of negative menthone in 3D in the chair form, we have to put the alkyl group in equatorial position. Yes, this is up equatorial, and this is down trans to one another equatorial. So this is the structure. Now notice that here is the carbonyl. Alpha to this carbon, we have two hydrogen in here, axial equatorial, and we have here this hydrogen axial. This is the model. If we clearly examine the faces of the carbonyl, this carbonyl, sp2, this part of the molecule planar, but the two faces of the carbonyl are distereotopic. You can put a plane of symmetry in there. So if we make the reduction, if the hydrogen is coming from down from reducing agent like sodium borohydride, the hydride comes from here. So this will be, the hydrogen will be down axial, and the OH will be up. OH is up equatorial, and this hydrogen is axial. If the hydride comes from up, so it will be the equatorial, and the OH will be the axial. So these are the expected product from the reduction of the menthone. One of them will be, okay, here is equatorial, that is the negative menthol, and OH axial, that will be the new menthol. This is up, OH is up, down, here up, down, down. That's how we draw it in the 2D. Now recall from lecture 27 the stereochemistry of the SN2 mechanism. For SN2, we have to have the two leaving groups, the one we are going to abstract and the one which leaves, has to be anti-coplanar. Okay, so theta will be, dihedral angle will be 180 in most cases, and rarely we find that theta could be 0. Okay, but mostly it's 180. This is what we recall. Now we'll go take this knowledge and apply it to our case. In menthol, the OH is equatorial, so this hydrogen is not anticoplanar to it. This hydrogen is not anticoplanar to it. This hydrogen is not anticoplanar to it. Here is equatorial, equatorial, equatorial. So this is the most stable conformer. This is the most stable conformer. If we flip it, that will be axial, 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 and that's not stable. And that is not stable. So, yes, we can see here that we have anticoplanar OH with alpha hydrogen in here. Okay? But that's not stable. We go to the new menthol. Here we have axial. We have here axial, axial. These two hydrogens on the alpha carbons to the carbon of the OH, okay, they are anticoplanar, and that is the most conformer, most stable conformer. This is equatorial and this is equatorial, the two alkyl group. If we make the other flip, other conformer, that's axial, so that's not stable. OH equatorial, none of these hydrogens are anticoplanar. So in the most stable conformer, yes, the OH and the hydrogen adjacent to it are anticoplanar. So in new menthol, if we protonate in the methanoic acid, we protonate here, okay, OH, then A minus will attack in E2, either take this hydrogen, the blue line, and form this alkene, or it can attack on this hydrogen, the red line arrow, okay, and form this alkene. This alkene is tri-substituted alkene. 1, 2, 3. And in this case, it is di-substituted alkene, which is stable, more stable. Of course, the tri-substituted alkene is more stable than the di-substituted alkene. So we expected methane structure to be that one. If we look for the reaction of alcohol with phosphorus pentachloride, the lone pair of oxygen will attack on the phosphorus, kicking the Cl out. Then again form this oxonium intermediate would be attacked with a Cl minus on this hydrogen or that one, and this is a very good leaving group now. So again, tri and di substituted, and this is the structure of methane expected, the tri substituted alkene. In case, in case of menthol, the hydrogens and OH are not anticoplanar. So instead of elimination reaction, alcohol and carboxylic acid together undergo what we call it nucleophilic acyl substitution. So the O will attack on the carbonyl carbon of the carboxylic acid, carboxylate carbon, forming this intermediates go, and the OH will take the hydrogen and leave to form the methanoate. In case of phosphorus pentachloride, the lone pair again will attack on the phosphorus, kicking Cl out. Instead of E2, SN2 reaction will occur. Chloride will attack, this time as a nucleophile from the back side, take this out. So instead of having here this equatorial, the chloride will be in the axial position, and that is the structure of the chloro compound. See you in the coming session. Bye.